Hi, welcome to the next video. And so in this video, we're just going to go over the material for the course. Okay, so 3.7, Chapter 4, Chapter 5, and Chapter 7. So we're going to go through a brief overview of lots of sections in the book. Okay, and so to do that, we're just going to do a bunch of problems. So let's start with on page 198 of the textbook. It's in the review section for chapter 3, 198, number 43. Okay, so page 198, number 43. And so so you need the textbook. For page 198, number 43, the problem is find the function f. Alright, so it gives you that f double prime of x is equal to 1 minus 6x plus 48x squared. And f of 0 equals 1, and f prime of 0 is equal to 2. Okay? So the goal is to find f. So let's find the most general antiderivative of f double prime of x. That's f prime of x. And so this is equal to x minus 3x squared plus 16x cubed plus c. Now find the most general antiderivative of f prime of x, which is f of x, and it's 1/2 x squared minus x cubed plus 4x to the fourth plus cx plus d. So now this is the most general function f. So now if you plug in f of 0, f of 0 is 1. And that's equal to all these terms with 0, and you get equals d. So you get d equals 1. So d equals 1. So I'm going to put that right here. F prime of 0, f prime of 0 is equal to 2. And plugging in 0 here, you get that's equal to c. So that means c is equal to 2. So here c is 2. And that's it. That's f. And so we found f. And this problem is done. Alright, so that's the first problem in our review. The next one . Okay, so next one is page 208, number 4b. So page 208, number 4b. So 208, 4b, and so it's repeat part A using left endpoints. And so we're going to estimate the graph under y equals the square root of x. From 0 to 4, using 4 approximating rectangles, and in this case, left endpoints. So we're going to use 4 approximating rectangles, and we're going to use left endpoints. And so when we do that, the first interval, the height is 0, because the height at 0 is 0. Here, the height is at x equals 1. Here, the height is at x equals 2. And here, the height is when x equals 3. So that's one line here, separate, okay? That's good. Okay, get rid of that. Good. So that's using 4 approximating rectangles and left endpoints for each subinterval. So the area is approximately the sum of these 4 approximating rectangles. So the first rectangle is 0 times 1. Plus the second rectangle, which is the height at 1, which is the square root of 1, times 1. Plus the height of the third one, which is the square root of 2, times 1. Plus the height of the third one, which is the square root of 3, times 1, which is equal to this 1. I'll write this way. 0 plus 1 plus the square root of 2 plus the square root of 3. That's equal to 1 plus root 2 plus root 3. Okay, so 4b is the area is approximately 1 plus root 2 plus root 3. That is an approximation using left endpoints and 4 approximating rectangles. So next problem. Page 222, number 34. Okay, so page 222, number 34. So for number 34, it says evaluate the integral by interpreting it in terms of areas. So it's a definite integral from -5 to 5 of x minus the square root of 25 minus x squared dx. So we're going to find this definite integral by interpreting it in terms of areas. So first let's think of it as a difference of two definite integrals. It's this definite integral minus this definite integral. Okay? And so we're going to find this area, this definite integral using areas, and this definite integral using areas, and then we're just going to subtract the two areas. Okay? So this one is represented by the graph y equals x. Y equals x from -5 to 5. Okay, so the area under y equals x from -5 to 5, this is the same as this, but this is negative area and this is positive area. So this definite integral is 0. Minus, now this area, so the square root of 25 minus x squared is the upper half of the circle with radius 5 centered at the origin. So this is y equals the square root of 25 minus x squared. Okay, and so this is the circle with radius 5 centered at the origin and the upper half of that circle. That's y equals the square root of 25 minus x squared. Okay, and so it's the definite integral from -5 to 5. So this is radius 5. So that's -5, that's 5. And so now it's the area of that region right there. That's half the area of a circle of radius 5. So this area is equal to half of a circle with center at the origin of radius 5. That's pi times 5 squared. So it's half of that. So it's half times 25 pi. So that's 25 over 2 pi. Alright? So this definite integral is 25 over 2 pi. And so it's 0, which is the first definite integral, minus 25 over 2 pi. Thus the answer is 12.5 pi. Okay? Negative 12.5 pi is the answer. And we're getting negative because this was 0 and that was negative. And area can be negative. Area is signed in calculus. What's below the x-axis is negative. What's above the x-axis is positive if you're going from left to right. Okay, so this is negative 12.5 pi. Okay, so the next one is page 231. Page 231, number 47. Okay, so number 47, find the general indefinite integral. So it's the integral of sine x over 1 minus sine squared x dx. Find the general indefinite integral. And so 1 minus sine squared x is cosine squared x. 1 minus sine squared x is cosine squared x. That's the trig. The trig identity is cosine squared x plus sine squared x equals 1. So 1 minus sine squared x is cosine squared x. And so this is equal to the integral of sine x over cosine squared x dx. Alright? And so let u equal cosine x. du is negative sine x dx. Okay? And so now you have a sine x dx, you're just missing the negative sign. So multiply the outside by -1 and the inside by -1, and you have negative sine x dx over cosine squared x. And so what that equals is negative the integral negative sine x dx is du. So this is du over cosine squared x is u squared. And so we get negative the integral of du over u squared. That's equal to negative the integral of u negative 2 du. And that's equal to u to -1 plus c. Okay? And so what that's equal to, u to -1, cosine x is u, so this is 1 over cosine x plus c. That's the final answer. Okay, so that's number 47 on page 231. It's an example using u substitution to find an indefinite integral. Calculate an indefinite integral using u substitution. All right, so let's keep going. Okay, so next is page 240, number 10. Okay, so page 240, number 10. And so for that one, we have used part 1 of the fundamental theorem of calculus to find the derivative of the function. So h of x is equal to the definite integral from 0 to x squared of the square root of 1 plus r cubed dr. Right? So the fundamental theorem of calculus says if you have a function g of x from the integral from a to x of f of t dt, then g prime of x is equal to f of x. Okay? That's what the fundamental theorem of calculus says. Now, if you take the fundamental theorem of calculus and you combine it with the chain rule, then you have this. Let's say you have g of x is equal to definite from a to a function h of x of f of t dt. Then g prime of x is equal to f of, instead of f of x, it's f of h of x, then times h prime of x. So g prime of x is f of h of x times h prime of x. So here, we're calling the function h now instead of g. So now the derivative of this function, h prime of x, is plugging the x squared, plugging this function into this function. So it's the square root of 1 plus x squared cubed times the derivative of that function times the derivative of x squared, which is times 2x. So h prime of x is equal to the square root of 1 plus x squared cubed times 2x. And so that's the derivative of that using the fundamental theorem of calculus combined with the chain rule. All right, so this is the rule. This is combining with the chain rule right here. That's the formula. That use that. Okay? And so I use this and I got the answer. All right, so that's number 10 on page 240. Okay, so on page 247, number 24. So page 247, number 24. So for number 24, evaluate the indefinite integral. So the indefinite integral is cosine of pi x. Cosine of pi divided by x over x squared dx. All right, so I'm going to let u equal pi over x, because what's weird is that there's a pi over x inside of the cosine. So I want to get rid of the weird input for cosine. So I'm going to let u equal pi over x. That means du is equal to negative pi over x squared when you take the derivative of it. Okay, negative pi over x squared dx. That's du. So we want to substitute du here. We have the x squared in the denominator and we have the dx here. We need a negative pi. So I'm going to put the negative pi there. So you have cosine of pi over x which is cosine of u. And I have a 1 over x squared dx already. I'm missing a negative pi, so I'm going to multiply by negative pi on the inside, and multiply negative 1 over pi on the outside, and they cancel. This is equal to negative 1 over pi, the integral of cosine of pi over x, which is u, times negative pi over x squared dx, which is du. So you get integral of cosine u du. This is equal to negative 1 over pi sine of u plus c. Right? Antiderivative cosine is sine plus c. So this is negative 1 over pi sine of what u is, which is pi over x plus c. And so the most general antiderivative of cosine of pi over x squared is negative 1 over pi sine of pi over x plus c. Okay, so that's the answer right there. All right, that's the explanation. Right, equal signs line up. Okay, so when I present this, I had the u part over here, the u substitution information here, and this is equals, and this lines up, and that's the answer. All right, so that's the next one. All right, so that's 3.7 and chapter 4. Those are problems in 3.7 and chapter 4. And so now we're going to start doing problems in chapter 5. So we go to page 260, number 23. Okay, so page 260, number 23. So for number 23 on page 260, we want to find the inverse of the function. So our function is y equals 1 plus the square root of 2 plus 3x. Okay, and so we want to find an inverse for that function. And so the first step is to solve for x explicitly in terms of y. So we're going to solve for x explicitly in terms of y. That means y minus 1 is equal to the square root of 2 plus 3x. Square both sides, y minus 1 squared is equal to 2 plus 3x. Subtract 2 on both sides, y minus 1 squared minus 2 is equal to 3x. And now you solve for x. X equals to y minus 1 squared minus 2 over 3. And so that's solving for x explicitly in terms of y. So we have that. Now switch x and y. Y is equal to x minus 1 squared minus 2 over 3. The new y is now f inverse of x. Okay, and so we now have f inverse of x. We want to express our inverse function where the input is x and the output is y. All right, so that's f inverse of x. We apply the 3 steps. Step 1, write y equals f of x. Step 2, solve for x explicitly in terms of y. Step 3, switch x and y. The new y is f inverse. Okay, so that's page 260, number 23. Good. Page 269, number 51. Okay. Okay, so on page 269, number 51, use logarithmic differentiation to find the derivative of the function. So y equals x squared plus 2 squared times x to the 4th plus 4 to the 4th. And we use logarithmic differentiation to find the derivative of the function. So take ln of both sides. Ln of the left side equals ln of the right side. Okay? Ln of the right, so step 1 is take ln of both sides and expand using laws of logarithms. So in addition, in step 1, we're going to expand the right side using the laws of logarithms. So this is equal to ln of, I'm going to write every step here, ln of x squared plus 2 squared plus ln of x to the 4th plus 4 to the 4th. And that's using the first law of logarithms, right? ln of a times b equals ln of a plus ln of b. Okay, so it applies that one. Now I'm going to apply the third law of logarithms and move the exponents in front. So this is equal to 2 ln of x squared plus 2 plus 4 times ln of x to the 4th plus 4. And so now I've expanded the right side as much as possible. So we have ln of y is equal to 2 ln of x squared plus 2 plus 4 times ln of x to the 4th plus 4. So that's step 1. This is step 1 of logarithmic differentiation. Taking ln of both sides and expanding the logs using the laws of logarithms. Step 1. Step 2 is differentiate implicitly with respect to x. So the left derivative of the left side here is with respect to x is 1 over y times y prime. That equals the derivative with respect to x on the right side, which is 2 times 1 over x squared plus 2 times 2x plus 4 times 1 over x to the fourth plus 4 times 4x cubed. Okay, so that's the derivative of the right side implicitly with respect to x. And okay, and now I'm gonna, and so then step 3, you just solve for y prime. So I'm gonna multiply both sides by y, and then the answer is y prime. So y prime is equal to y, which is given to us as x squared plus 2 squared times x to the fourth plus 4 to the fourth, that's y, times everything else. This is times 4x over x squared plus 2 plus 16x cubed over x to the fourth plus 4. Okay, so I'm just writing it in a more condensed way. It's the same thing that's already here. Okay, so that's y prime, and so step 2 was here. Step 2 was differentiating, and step 3 was solving for y prime. And so those are the 3 steps right there. And we're done. So that's number 51 on page 269. It's a logarithmic differentiation example. All right. All right, next problem. Okay, so next is page 274, number 36. Page 274, number 36. Okay, so page 274, number 36. Differentiate the function. So our function is f of t is equal to sine squared of e to the sine squared t. All right, so let's find the derivative. So f prime of t is equal to, so this function is squared. So it's going to be 2 times sine of e to the sine squared t, raised to the first power, times the derivative of sine, which is cosine, evaluated e to the sine squared t, times the derivative of e to the sine squared t, which is e to the sine squared t, times the derivative of the x1 sine squared t, which is 2 sine t, continue this down here, times 2 sine t times the derivative of sine t, which is cosine t, and that's the answer. So it's this times this also, multiplying continues. This whole thing is f prime of t. Okay, so it's a composition of a lot of functions. That expression is a composition of a lot of functions, and so you're repeatedly applying the chain rule to get this derivative. Okay, one function is that when you have, one form was that when you have the derivative of a function to the nth power, like f of x to the n, then that's equal to n times f of x to the n minus first power times f prime of x. So you need to know that formula to calculate. And so we do this at the beginning because you have sine squared of something. So the derivative of sine squared of that is equal to 2 times sine of that function to the first power times the derivative of sine of that, which is cosine of that, times the derivative of that, which is e itself, e to this, times the derivative of sine squared, which is 2 sine t times cosine t. Okay, so this is applying the chain rule repeatedly because you have a composition of a lot of functions that you're taking the derivative of. Okay, so this is number 36. Okay, this is a bit of a difficult problem, right? So I went over using the chain rule, right? And so if you're lost with this example, the best way, I guess, to see this would be look back at other chain rule problems, other times where you had a composition of functions and you take a derivative, because this is a bit of a hard one. Okay, yeah. All right, let's keep going. Next page is 282. Page 282, number 31. So we have page 282, number 31. And so differentiate the function. So y equals x dx. Okay, so first you take ln of both sides. So ln of y equals ln of x dx, which equals x ln x. Okay, so I took ln of both sides and I expanded this using the laws of logarithms. This is the third law of logarithms. And so step one, we have ln of y equals x ln x. Differentiate both sides implicitly with respect to y. You get 1 over y times y prime is equal to the derivative of this with respect to x. That's the first function times the derivative of the second, plus the second function times the derivative of the first. That's the product rule, right? And now, so we differentiate, now solve for y prime. Y prime is equal to y, which is x to the x, times that, which is 1 plus ln x. And that's it. Y prime is equal to x to the x times 1 plus ln x. All right, that's number 31. All right, so let's keep going. So next is page 290. Number 8. Okay, so page 290, number 8. Okay, so page 290, number 8. Strontium 90 has a half-life of 28 days. Okay, so your half-life is 28 days. That means that every 28 days, the amount of strontium 90 you have, it halves. Okay, so A. The mass of a sample is 50 milligrams initially. Okay, find a formula for the mass remaining after t days. Okay, so our formula for the mass is m of t is equal to m of 0 e to the kt. And so this is the formula we always use. We're assuming our function, the growth rate is proportional to its size. Okay, and so the only solutions are m of t equals m of 0 times e to the kt. This is the initial mass, so this is equal to 50 e to the kt. So the half-life is 28 days. That means if we plug in 28 for t, that means that the amount is halved after that time. If we started with 50, then after 28 days, there's 25 left. So m of 28 is 25. And so that has to equal plugging in 28 for t here. So this is equal to 50e to 28k. And so 25 is equal to 50e to the 28k. Divide both sides by 50, you get 1/2 is equal to e to the 28k. That implies you take ln of both sides, you get ln of 1/2 is equal to ln of that, which is 28k. And the ln and e cancel. And that implies that k is equal to 1 over 28 ln of 1/2. So k is equal to 1 over 28 times ln of 1/2. And so that is the relative growth rate. K is the relative growth rate. And so the problem was to find a formula for the mass after t days. So m of t is equal to 50 e to the k, which we found, 1 over 20, ln of 1/2 divided by 28. That's k, and then times t. So m of t is equal to 50 e to the ln of 1/2 over 28t. That's the population, that's the amount of mass after t days. That's part A. All right. Part B is find the mass after 40 days. So this is after t days, so you just plug in 40 for t. That's the mass after 40 days. So this is equal to 50e to the ln of 1/2 over 28 times 40. All right, and you put that in a calculator and you get the answer. Right? 50 times e to the ln of 1/2 over 28 raised to the 40th power. Okay, so that's part B. C is how long does it take for the sample to decay to a mass of 2 milligrams? Okay, so let me, I'm going to erase all this stuff here. We don't need it. So for part C, we want the time it takes for m of t to equal 2. Right, we want to know after how many days does the mass become 2 milligrams. So m of t is 50e to the ln of 1/2 over 28t. And you set it equal to 2 and you solve for t. So divide both sides by 50, you get e to the ln of 1/2 over 28t is equal to 2 over 50, which is 1 over 25. Take ln of both sides. So you get ln of 1/2 over 28 is equal to ln of 1 over 25. I just took ln of both sides, and the ln and e cancel, and you're left with the exponent, which is times t there. Solve for t, just multiply both sides by the reciprocal of this fraction. So multiply both sides by 28 over ln of 1/2. This is equal to ln of 1 over 25 times 28 over ln of 1/2. All right, and so that's the answer. T is equal to, you can plug that in the calculator and get the answer. T is ln of 1 over 25 times 28 over ln of 1/2. That's the amount of time it takes for the mass to decay to 2 milligrams. That's how many days. Okay, and then part D, sketch the graph. Okay, and so you put the graph into your calculator and it graphs it, all right? Okay, so let's just draw a graph. I don't want to go over that. You can just use your calculator and just put that into the function. Okay, so now next. So page 297, number 17. So page 297, number 17. Find the derivative of the function. So 17 is y equals tan inverse x squared. And so let's find the derivative. Let's find y prime. Y prime is 2 times tan inverse x to the first power times the derivative of tan inverse x. Right? Because you know that the derivative, again, d dx of f of x to the n is equal to n times f of x to the n minus 1 times f prime of x. And so in this case, f of x is tan inverse x, and n is 2. So the derivative of tan inverse x squared is 2 times tan inverse x to the first power times the derivative of tan inverse x. Again, d dx of tan inverse x squared is equal to 2 times tan inverse x to the first power times the derivative of tan inverse x. That's right there. Okay, and so then that's equal to 2 tan inverse x times the derivative of tan inverse x, which is 1 over 1 plus x squared by the formulas for derivatives of inverse functions. And that's it. That's y prime. 2 tan inverse x times 1 over 1 plus x squared. Okay, so that's number 17. All right, so that is now, those are the problems in chapter 5 I want to go over. All right, so the next problems I'm going to go over are in chapter 7. Okay, so page 375. So page 375, number 18. So page 375, number 18. Sketch the region enclosed by the given curves and find its area. Okay, so page 375, number 18. We have y equals the absolute value of x, which looks like that. That's the graph of y equals absolute value of x. And then you have y equals x squared minus 2. So y equals x squared minus 2, and then it looks like that. Okay, it's just the graph of y equals x squared translated down by 2 because there's a minus 2 there. So the bottom point here is when x is 0, y is negative 2. This is the origin. And then what are the intersection points of these two graphs? It's when absolute value of x is equal to x squared minus 2. So there's two cases, right? Case 1 is when x is greater than or equal to 0. In this case, we're looking at this point. That means that the absolute value of x is x, and it equals x squared minus 2. So 0 is equal to x squared minus x minus 2. And you solve for x, and you get, what am I doing here? Find its area, okay. So then, solve for x using the quadratic formula. X equals negative b plus or minus the square root of, it's negative b, so it's negative 1 plus minus the square root of negative 1 squared minus 4 times a times c over 2 times a. That's equal to 1 plus or minus the square root of 9 over 2. Okay, so that's equal to, if it's a plus, it's 1 plus 3 over 2. That's 4 over 2, that's 2. If it's a minus, it's 1 minus 3 over 2, which is negative 1. And so we solve for x, and we get x equals 2 and x equals negative 1. But we only looked at x positive. So negative 1 is a reject answer. We get x equals 2. So maybe I could have done this without all this work. When x is 2, y is 2 for both functions. All right? I'm seeing symmetry here. So case 2 would be x negative. But let's just try x equals negative 2. So when x is negative 2, that's 2. And that's also 2. So that's the other intersection point. So the two intersection points are 2, 2 and negative 2, 2 of these two graphs. And so we're looking at the region bounded by the curves of those two graphs. So that shaded region is the region we want to find the area of. Okay, so to do that, let's draw one of our rectangles there. And the rectangle is showing us what the top function is and what the bottom function is. And we're integrating with respect to x because the width is a change in x values. So we're integrating with respect to x, and the top function is y equals the absolute value of x, and the bottom function is y equals x squared minus 2. And so the area is equal to the definite interval from the leftmost x value, which is negative 2, to the rightmost x value, which is 2, of the top function, which is the absolute value of x, minus the bottom function, which is x squared minus 2 dx. All right. And so if you notice here, this is an even function. The absolute value of x minus x squared minus 2 is an even function. That means that if you plug in the x there, it's the same as if you plugged in negative x. So for instance, the absolute value of negative x minus negative x squared minus 2 is equal to the absolute value of x minus x squared minus 2. So if you put an x or negative x, they're equal, they're the same. The absolute value of negative x, right? And you take the absolute value of x and you square x, and so it'd be plus or minus x there. And so it has symmetry about the y-axis. That means that the area on the right side of the y-axis is the same as the area on the left side of the y-axis. Right? It's just a mirror image of itself about the y-axis. And so finding the definite interval from negative 2 to 2, because this is the negative of that, finding the integral from here to here means you could just go from 0 to 2 and then say twice that. Right? So instead of finding the entire area, we could find half the area and then multiply it by 2, because there's a symmetry about the y-axis by the type of function we're integrating. This is equal to 2 times the integral from 0 to 2 of the absolute value of x minus x squared minus 2. And so why did I do that? That's because now when I'm looking at the absolute value of x, it's only from 0 to 2, not from -2 to 2. That means the absolute value of x is always x from 0 to 2. So I can substitute the absolute value of x for x. This is 2 times the definite interval from 0 to 2 of x minus x squared minus minus 2 is plus 2 dx. And so when I calculate this differential, you just multiply it by 2, and then that's the answer. Okay? And so what is the value of that differential times 2? Is equal to 2 times x squared over 2 minus x cubed over 3 plus 2x evaluated from 0 to 2. And so when we calculate that, you get 2 minus 8/3 plus 4. Let me just calculate it real quick. This is 2 minus 8/3 plus 4, and then minus 0. It's that times 2. So that's equal to 6 minus 8/3. That's 10/3 times 2. That's 20/3. Okay? That's 20/3. So this is equal to 20/3. Okay, so that area is equal to 20/3. And that's the answer. Okay. Okay, so that's finding the areas between curves in 7.1. The next problem. Okay, page 385, number 16. So page 385, number 16. So page 385, number 16. There's a region bounded by the given curve, so I'm going to rotate it about the specified line, x equals 1. So x equals y squared. X equals 1, and we're going to rotate about x equals 1. So let's do that. So first let's graph these two graphs. It's always a little annoying when it's x in terms of y, but x equals something. So x equals y squared is a parabola facing to the right, like that. That's x equals y squared. And then x equals 1. X equals 1. That's easy. Okay, x equals 1 is this vertical line. I was thinking of something else. Okay, x equals 1 is right there. Alright, so that's the region bounded by x equals y squared and x equals 1. And you rotate about x equals 1, the same line. And so you draw the mirror image of that shaded region. First you can draw the mirror image of it without worrying about the three-dimensional part. Then just draw the picture of it being rotated. We're rotating this about x equals 1. So this circle here is kind of how you can illustrate to the person looking at the picture that it's now a three-dimensional object. I drew this arrow around x equals 1 to indicate that to the reader that we're rotating that shaded region around the line x equals 1. Okay, so we have our three-dimensional object there, and so we want to find the volume of that. Find the volume. Okay, so the volume is going to equal, so we're going to decide how we're going to find this volume. And so let's find the volume using washers. And so let's use this middle circle as our washer, that thickness, okay? So the thickness here is delta, so you see this thickness has like a height, is a change in y values, the thickness. So this is an integral with respect to y. Okay, so this is a definite integral from the lowest y value to the highest y value. Well, that's where x equals y squared meets x equals 1. Well, when x is 1, y squared is 1 when y is plus or minus 1. This is 1 comma 1 and 1 comma negative 1. So y values are ranging from negative 1 to 1. So the volume is definite from negative 1 to 1 of an integral with respect to y. Now, let's find the washers. So the radius of the washer here, the radius is equal to the, oh, I don't want to talk about the radius there. I want to talk about the radius here. So actually, let me draw another washer, just so it illustrates better. This is the radius of the circle, and it has this thickness. That's delta y. Okay, now here's the radius of this washer guy. Well, the radius, so this distance here, right, that distance here is the x distance of a point on the curve. And so we know the x coordinate of a point on the curve is y squared. So this distance is y squared. Okay, y squared is this distance. This whole thing is 1. And so if you take 1 and you remove from it y squared, you're left with the radius. So it's 1 minus y squared. So the radius of our washer is 1 minus y squared. And so the, I'm sorry, not, disc, sorry, the disc, right? This is a disc, not a washer. That's a disc, right? And the area of a disc is pi r squared, right? Which is the area of a circle. And so this is pi times the radius squared. The radius is 1 minus y squared, And so the volume is definition from -1 to 1 of pi times 1 minus y squared dy. This is equal to pi times the definition from -1 to 1 of 1 minus y squared. And that's the same as 1 minus 2y squared plus y to the 4th. That's just multiplying finding 1 minus y squared. And we get that. Now find an antiderivative. Use the evaluation theorem. It's equal to pi times an antiderivative, which is y minus 2/3 y cubed plus 1/5 y to the 5th. An antiderivative evaluated from the lower limit of the definite interval to the upper limit of the definite interval, from -1 to 1. And so this is using the evaluation theorem. And so now we just calculate that and we get our final answer. This is equal to pi times, you plug in 1, you get 1 minus 2/3 plus 1/5. Subtract from that, plug in -1. Now when you plug in -1, you get the negative of that. So you're going to subtract the negative of that. And so that means you're really just taking 2 of them. So it's times 2 of that. You're taking this quantity and subtracting the negative of it. So that means you're adding another one. So that means you now have 2 of them. Okay, and so this is equal to 2 pi times 1 minus 2/3 plus 1/5. So 1 minus 2/3 is 1/3. 1/3 plus 1/5 is 8/15. So that's 2 pi times 8/15. So this is 5/15 plus 3/15. That's 8/15. And so 2 pi times that, and that's 16/15 pi. Alright, so we have 16/15 pi. That's the final answer. So that's the volume of that 3-dimensional object. That's how much space that 3-dimensional object takes up. 16/15 pi. Okay, so that's number 16 on page 385. Next one. Okay, that's page 385. Page 391. So page 391, number 15. Page 391, number 15. We're going to use cylindrical shells to find the volume. Okay, so here for number 15, it's y equals x to the 4th, comma, y equals 0, comma, x equals 1, about x equals 2. Okay, so we're going to take the region bounded by those 3 curves, rotate it about the line x equals 2, and find its volume. Let's draw the 3 curves here. So you have y equals x to the 4th. That looks like that. Okay. Y equals x to the 4th. This is the y-axis. This is the x-axis. When y is 0 is the x-axis, and x equals 1 is that vertical line right there. That's what x equals 1, that's y equals 0. And so what's bounded by those three curves is this region right here. Okay, I'm going to rotate that about the line x equals 2. That's the line x equals 2. And so now we're going to take that point and reflect it. Take this point and reflect it. Take this point and reflect it. Reflect that curve there to that curve. Reflect this vertical line to that vertical line. And so now this is the mirror image of that. And now just draw a circle around each corresponding point. So two corresponding. So these two, draw a circle connecting those two. Draw a circle connecting those two. And draw a circle connecting those two. And draw it with confidence. So just when you start drawing the circle, just keep drawing the circle until you're done. And then see what happens. Excuse me. So, okay, so there's your three-dimensional object. And so we're going to use the method of cylindrical shells to do it. So to use the method of cylindrical shells, think about the direction of your washer. Well, so I can sweep across the shaded area with vertical line segments. Okay, so if you thought of vertical line segments, you could, where the top function is y equals x to the fourth and the bottom function is y equals 0. You could have these vertical line segments from left to right sweep across your shaded area. For each vertical line segment, you could rotate it around the line x equals 2, just like everything else, and that would give you a cylindrical shell for each vertical line that you rotated around x equals 2. Right? So just like all the vertical line segments make up the entire shaded area, their rotations make up the entire three-dimensional object, where you're taking your entire three-dimensional object and subdividing it into the cylindrical shells from each separate line segment. Okay? And so we're using those, you use those, so the actual volume is a limit of infinitely many cylindrical shells that when you add up their volumes, you get closer and closer to the actual volume. So the volume is a limit of a sum of cylindrical shells. But to calculate it, you just use our formula. So the volume is equal to the definite integral from the leftmost, because our vertical line segment, its width is the change in x values, right? And so that means you're integrating with respect to x. And so you're integrating from the leftmost x value, which is 0, to the rightmost x value, which is 1. You're only looking at the original shaded region that was bounded by original curves in order to determine the range of x or y values. Here it's x. So it's from x equals 0 to x equals 1. Now, what is the volume of a cylindrical shell? You put it here. So it's 2 pi times the radius. Well, the radius of your cylindrical shell is this. Okay, it's the length, that's the radius of your cylindrical shell. Well, the radius is this distance, right? This point is x comma y, and it's a point on y equals x to the fourth. But this distance, you're integrating with respect to x. This distance is x. This distance is the x coordinate of that point. This entire distance is 2. And so if this is x and this whole thing is 2, if you take 2 and subtract x, you're left with the radius. So the radius is 2 minus x. So 2 pi r is 2 pi times 2 minus x. And now you take the height of the function. And the height of the function is just the height of the function y equals x to the fourth. Right? That's the height. This vertical line is the height of your function y equals x. So the height is y, which is x to the fourth. So the height is x to the fourth. And so you get that you get 2 pi r h there. And so now this definite integral is the volume of that three-dimensional shape. So it's 2 pi times definite integral from 0 to 1 of 2 minus x to the fourth dx. Okay, so now let's find this. This is equal to 2 pi times definite integral from 0 to 1 of 2 minus x times x to the fourth. That's 2x to the fourth minus x to the fifth dx. And so now you find an antiderivative of the integrand function. This is 2 pi times an antiderivative, which is 2/5 x to the fifth minus 1/6 x to the sixth, and you evaluate from the lower limit 0 to the upper limit 1. And so when you calculate that, you get 2/5 minus 1/6 minus 0. So you get 7/30 there times 2 pi. So you get 14/30 pi. So it's just, you calculate that, and you get 7/15 pi in simplest form. Okay, so that's 7/15 pi. And 12/30 minus 5/30 is 7/30 times 2, 14/30 and pi. That's 7/15. Good. So that's it. Okay, so that's just this times this, which is 7/15. All right, and so that's using the method of cylindrical shells, solving for the radius and knowing what the height is, right? 2 pi rh. 2 pi r is 2 minus x. The height of the function is h, which is x to the fourth. So that's page 391, number 15. Okay. Okay, so page 397, number 10. So page 397, number 10. Find the exact length of the curve. So number 10 is x equals y to the fourth over 8 plus 1 over 4y squared, where 1 is less than or equal to y less than or equal to 2. Okay, so we're going to find the exact length of this curve. So this is capital L is equal to definite integral from 1 to 2 of the square root of 1 plus dx dy squared dy. So the fact that you have a range of y values and a function of x equals an expression of y means you want to use the arc length formula with differential with respect to y. So this is L equals differential from c to d of the square root of 1 plus dx dy squared dy. That's the arc length formula where you calculate it as an integral with respect to y. So that's what we're going to use here. Y is the range of values are for y, and you have x solved in terms of y. Everything is in terms of y here. So we want a definite integral in terms of y. So we're using this version of the arc length formula. Okay, so we want to find dx dy and then square it and plug it in here. So what's dx dy? Dx dy is equal to the derivative with respect to y of that. That's 1/2 y cubed minus 1/4 y to negative 1. Okay, so that's dx dy. And dx dy squared is squaring that. Dx dy squared is the square root of that. And the square root of that is 1/4 y to the sixth minus 1/4 y squared plus 1/16 y to negative 2. So dx dy squared is that. Okay, so you square that and you get this. Okay, so you square that and you get this. Right? And then when you add 1 to that, that's what's in the square root. What's in the square root is 1 plus that. So let's add 1 to that. 1 plus dx dy squared is equal to 1 plus that expression. 1 plus 1/4 y to the sixth minus 1/4 y squared plus 1/16 y to the negative 2. Okay. Make sure I did the multiplication right. That's 1/8. Okay, good. So now I need to think, what I'm going to think of is how can this is 1 plus dx dy squared here, right? Which is that. How can I express this as something squared? Let's see. I had the 1/4 y cubed, y to the sixth. That's the highest power of y. So let's think of the square root of that, 1/2 y cubed. Now I want to add something to that so that that thing is equal to that plus something squared. So plus or minus. There could be a plus or minus symbol there. Maybe minus 1/4 y to negative 1. Let's try that. Okay, so we have 1/2 y cubed minus 1/4 y to negative 1. And you multiply it by itself. That's equal to this times this, which is 1/4 y to the 6th minus this times this is minus 1/8 y squared. This times this is minus 1/8 y squared plus this times this is plus 1/16 y to the negative 2. No, okay, wait. So, well, that's this again. Never mind. So no, that won't. Don't want that. Check my math. We have dx dy, which is 4 1/2 y cubed plus derivative, antiderivative of that. Oh, this is where the problem is. You have y negative 2. Y to negative 3. It's y to negative 3 there. Because this is 1/4 y negative 2, that term. And derivative of that is plus. The derivative of that is negative 1/2 y to negative 3. 1/4 times negative 2. Negative 1/2 times y to negative 3. Okay, so I have to fix that. Dy dx squared is this squared. So this is 1/4 y to the 6th minus 1/2 plus 1/4 y to negative 6. So if you take this thing and you square it, if you square that, you get this. Good, so we get that. Okay, now this is looking better. So 1 plus dx dy squared is 1 plus that. That's 1/4 y to the 6th plus 1/4 y to the negative 6. And then there's a minus 1/2 and a plus 1, so that's plus 1/2. All right. So now this thing, which is this, is 1/2 y to the 3rd plus 1/2 y to the negative 3rd in parentheses squared. You square this out, you get this square, which is this square, which is that, and then this times this is 1/4, and there's 2 of them, so this is plus 1. So this is that squared. So this is that squared, and the trick is take the square root of this and the square root of that and add them. And when you square the sum, the plus 1/2 is the actual thing there. Okay, so the square root of this, which is this, plus the square root of that, close parentheses, square it, and you'll get this plus the 1/2 there. All right, that's the trick. It works sometimes. Okay, other problems you need other kind of solutions. Okay, we did other example where it was u substitution instead. So you may need to use u substitution in a problem like this also. Okay, so then you define from 1 to 2 of the square root of this, which is 1/2 y cubed plus 1/2 y to negative 3 squared dy. Okay? Okay, so if you take the square root of something squared, they cancel. And you're left with just, this is the definition from 1 to 2 of 1/2 y cubed plus 1/2 y negative 3 dy. Okay, and the square root and the square cancel, and you get that. So this is equal to, I'm going to factor out the 1/2. This is 1/2 times the antiderivative what's left. So this is 1/4 y to the 4th minus 1/2 y to negative 2. Evaluated from 1 to 2. This is equal to 1/2 times, plugging in 2, you get 4 minus 1/8. That's plugging in 2. Minus plugging in 1, and that's 1/4 minus 1/2. Okay, so this is negative 1/4. So minus negative 1/4 is adding a fourth, it's adding 2/8. Minus 1/8, that's 1/8. so that's 33/8. So you get 33/16. Let's see, that's the calculation on that. Okay. Just to check. 1/4 minus 1/2 is -1/4, minus -1/4 is +1/4, it's plus 2/8. 2/8 minus 1/8 is 1/8. 4 1/8 is 33/8. 33/8 times 1/2 is 33/16. That's it. Okay, and so the length of that curve from y equals 1 to y equals 2 is 33/16. So that is number 10 on page 397. All right, and so these are problems to go over. These were problems in chapter 7. So we went over a problem in 3.7, problems in chapter 4, problems in chapter 5, and problems in chapter 7. All right. The best way to study, to learn more in math, is just to do more problems. And so I'm hoping that with all these problems being shown to you, being assigned to you, seeing the solutions of lots of problems, a lot of it's getting in your head, and you're able to do more math problems. And so the more problems you can solve, the better you are. So just need to keep doing more problems, keep doing more math. Okay, so let's do another problem. Let's have another one. Page 425. Page 425, number 10. Here's another problem. Okay, so this one video doesn't cover everything, right? So these are some of the problems that you need to know how to do. All right, there's also the review lesson too. Okay, so page 425, number 10. Find the solution of the differential equation that satisfies the given initial condition. dy dx is equal to ln x over xy, where y of 1 is equal to 2. And we want to solve that with the given initial condition. This is y dy is equal to ln x over x dx. And so I put everything with y on one side and everything with x on the other side. And you integrate both sides. Okay? So let u equal ln x. du is equal to 1 over x dx. So we have ln x, which is u, and 1 over x dx, which is du. So the right side is the integral of u du. Okay, and so we have the integral of y dy is equal to the integral of u du. So that means y squared over 2 is equal to u squared over 2 plus c. U is ln x. So this is ln x squared over 2 plus c. And now we need to find c that satisfies our given initial condition, y of 1 equals 2. Plug in x is 1, y is 2. So you get, so we have this is equal to this. And so y is 2. 2 squared over 2 is 2. 2 is equal to ln of 1 squared over 2 plus c. ln of 1 is 0. So that's c. So 2 is equal to c. c is equal to 2. And so our final answer for this problem is that a solution of this differential equation that satisfies the initial condition is y squared over 2 is equal to ln x squared over 2 plus c, which we found is 2. Okay, so here we solve for y implicitly in terms of x. And so solving for y implicitly in terms of x is a legitimate way to find a function y that satisfies a differential equation. Okay? You could either solve for y explicitly or implicitly. And so here we solve for it implicitly. Okay, so that is a solution to this initial value problem. All right, so we went over a problem, I think in every section, we went over one problem in every section we went over in the class today. So this is a quick overview of a lot of the material that we went over in the semester. Let's just do another problem. So how about okay, so let's do this problem. On page 314, number 49. So page 314, number 49. So on page 314, number 49, it says find the nth derivative of f at x. Find the nth derivative of f. Okay? And you're given that f of x is equal to 2 to the x. So you want to find the nth derivative of f. So we're going to use this formula. d dx, the derivative of 2 to the x, is equal to 2 to the x ln of 2. It comes from the more general formula, d dx of a to the x equals a to the x ln a. And so where here a is a constant, right? So in our problem, a is 2. So d dx of a 2 to the x is 2 to the x ln 2. So the first derivative of f, we've written already, it's 2 to the x ln 2. And now we're just going to repeatedly apply this rule to find subsequent derivatives. So the second derivative of f at x is now the derivative of 2 to the x, which is 2 to the x ln 2 times the constant ln 2. And so this is equal to 2 to the x times ln 2 squared. So the second derivative of f is equal to 2 to the x ln of 2 squared. The first derivative of f was 2 to the x times ln of 2 to the first power. And the zeroth derivative of x is 2 to the x times ln of 2 to the 0 power. Anything to the 0 power is 1. And so I can multiply it by ln of 2 to the 0, and it's like multiplying by 1. I'm not changing the value. Now if I take the third derivative of f, it's the derivative of 2 to the x, which is 2 to the x ln 2, times the constant ln 2 squared. That's equal to 2 to the x times ln 2 cubed. Okay, so the 0th derivative of f is 2 to the x times ln of 2 to the 0. The first derivative of f is 2 to the x times ln of 2 to the first. The second derivative of f is 2 to the x times ln of 2 squared. The third derivative of f is 2 to the x times ln of 2 cubed. And so continuing, you get the nth derivative. You can intuitively, so you can reason that what's probably happening here is that the nth derivative of f at x is equal to 2 to the x times ln of 2 to the nth power, and that's it. Okay, so the nth derivative of f at x is equal to 2 to the x times ln of 2 to the nth power. Right? The power of the order, right? The derivative that you're taking corresponds with the power of ln of 2. So the nth derivative of f is 2 to the x times ln of 2 to the n. And so that is the solution to 49. Find the nth derivative of f at x. 2 to the x times ln of 2 to the n. Okay? Okay, so we'll stop here. And so we saw a lot of problems. We saw the solutions to 2, 4, 6, 8, 10, 12, to 18 problems. Okay? So hopefully that gives you an overview of some of the material for the course. But we only did about basically one problem per section in this video. So that doesn't cover all the types of problems in each section, right? We did one extra problem in this section, which is, well, this is a review problem from chapter 5. Okay. All right. So just keep doing problems. That's the most important thing. All right. And good luck studying.